Hello everyone, I am Punyashri KP. Today, me and my teammates are going to explain our mini project that is Nyquist criterion verification. Have you ever wondered how aeroplanes remain stable in the air? Or how robots move accurately without losing control? Or how machines in the industries work smoothly for hours without a failure? Behind all these systems, there is one important concept called stability. Because if a system becomes unstable, even a small error can make an entire system fail. So, engineers use special techniques to check stability before implementing any systems in real life. One such powerful technique is the Nyquist stability criterion is a graphical frequency domain method used to control the systems to determine whether a system is stable or unstable. It works by analyzing the Nyquist plot, which is obtained from the frequency response of the open loop transfer function. The stability of the system is determined by observing the encirclement of the critical point in the complex plane. If the plot does not encircle the critical point, the system is stable. If it encircles the point, then the system becomes unstable. Further will be continued by Rakshita E. Now let us understand the program step by step. This program is written in GNU octave to verify the Nyquist stability criterion for both stable and unstable systems. First one is CLC. This command clears the command window. It removes all previous output from the screen so that the current program output appears clearly without confusion. Next is clear. This command removes all variables stored in memory. It ensures that old variable values does not affect current execution of the program. Next is close all. This command closes all previous open and figures windows. So whenever we run the program, fresh graphs are generated. Next is omega or W is equal to log space minus 2 comma 2000. Here, we define the frequency range. The log space function generates logarithmically spaced frequency values from 10 to the power of minus 2 to 10 to the power of 2. Using 2000 samples points, a large number of points gives smoother Nyquist plot. Next is j omega. That is jw is equal to 1I into w. Here, frequency variable is converted into complex form, j omega, where j represents the imaginary term and omega represents the angular frequency. Next is, we have to give the values, that is k is equal to 5. K represents the gain of the system and gain affects the magnitude and shape of the Nyquist plot. Next, G1 is equal to k divided by j omega into j omega plus 1 into j omega plus 2. These lines defines the transfer function of the stable system. Mathematically, the transfer function is g of s is equal to k divided by s into s plus 1 into s plus 2. The poles are located at 0, minus 1 and minus 2. Since all the poles are left half plane or on the imaginary axis, the system behaves stably. Next is RE1, that is equal to real of G1. This command extracts the real part of the transfer function response. The real values are required to plot the Nyquist graph on the x-axis. Next is IM1 is equal to image of G1. This command extracts the imaginary part of the transfer function response. These values are plotted on the y-axis. Next is figure. This command opens the new figure window for plotting the stable system graph. Next is plot RE1, IM1, line width, 2. This line plots Nyquist curve for the positive frequencies. The graph is drawn using real imaginary components with the line width 2. And hold on. This command holds the current graph. It allows multiple plots to appear in the same figure window. Next is octave plot RE1, imaginary 1 and line width 2, minus imaginary. This line plots mirror image of the Nyquist curve. It represents the negative frequency response. Next is plot minus 1, 0, R0, mark size 8 and line width 2. This line marks the critical point, that is minus 1, 0 using red circle. This point is extremely important because system stability is determined based on its encirclement. Next, grid on. This command enables the grid on the graph. The grid improves the readability and helps in analyzing the plot clarity. Next, X label real axis. This command labels the X axis with the real axis. Next is Y label, that is imaginary axis. This command labels the Y axis as the imaginary axis. Next is the title plot stable system. This line gives a little title to the graph indicating that it represents the stable system, and further will be continued by the Punyashri Sage.
I am Punyashri. Next will be ligand positive frequency, negative frequency -1 to 0. This command adds the ligand to the graph. The ligand helps to identify positive curve, negative frequency curve and critical point. Next is X line of 0, Y line of 0. This command draw the horizontal and vertical axis. This improves the visualization of the Nyquist plot. G2 equals to K by J omega into J omega minus 1 into J omega plus 2. This line defines the transfer function of the unstable system. The mathematically G of S equals to K by S into S minus 1 into S plus 1. Here, G of S equals to K by S into S minus 1 into S plus 1. Here, one pole is located at plus 1, which is lies on the right half plane. Therefore, the system become unstable. RE2 equals to real of G2. IM2 equals to image of G2. This command extract the real and imaginary part of unstable system response. Next is figure. This command opens the new figure window for plotting the unstable system graph. Plot RE2, image 2, line width 2. This line plots the Nyquist curve of the unstable system using positive frequency value. Hold on. This command holds the current graph so that additional part can be drawn to the same figure. Next is plot RE2 minus IM2 line width, 2. This line plots the mirror image for the Nyquist curve representing the negative frequency response. Next is plot -1, R0, mark size, 8, line width, 2. This command marks the critical value -1 to 0 using red circle. The stability of the system is determined based on the encirclement of the point. Grid on. This command enabled to the grid for better visualization of the graph. X label real axis. This labels the x-axis for as real axis. Y label imaginary axis. This line labels the y-axis for as imaginary axis. Title Nyquist plot unstable system. This command gives the title for the unstable system Nyquist plot. Ligand positive frequency, negative frequency -1 to 0. This line adds the negative ligand. This line adds the ligand to identify positive frequency curve, negative frequency curve, and critical point. Next one is X line of 0, Y line of 0. This command draw the horizontal and vertical to improve the graph stability, graph readability. Further, we'll conclude by Rakshita.
Hello everyone, I am Rakshita. After executing the program, two Nyquist plots are obtained. These are the two outputs, one for the stable system and another for the unstable system. In the stable system plot, the Nyquist curve does not encircle the critical point. Therefore, the system is stable. In the unstable system plot, the Nyquist curve encircles the critical point. Hence, the system becomes unstable. The graph clearly shows the difference between stable and unstable system using frequency domain analysis. Finally, in this project, the Nyquist stability criterion was successfully verified using GNU octave. Nyquist plots were generated for both stable and unstable systems, and system stability was analyzed based on the encirclement of the circle point. The project helped in understanding the frequency response analysis and graphical stability verification in control system. Thank you for watching.